The simplest capacitor consists of two metal plates located at a certain distance in parallel to each other. The space between the capacitor's plates can be filled with air or solid dielectric. The larger the area of such plates and the smaller the distance between them, the bigger is the electronic capacitance of the capacitor. If the capacitor plates are connected with a DC power supply, the charges of such power supply will move to the capacitor, and the capacitor charging current will start flowing in the circuit. As the capacitor charge increases, the voltage on it will also grow, and the voltage difference between the capacitor and the power supply will begin to decrease. This will also lead to a decrease in the charging current. When the voltage on the capacitor reaches that of the ideal voltage source, the voltage difference between the power supply and the capacitor will be equal to 0, and therefore there will be no charging current anymore. In other words, accumulation of charge on the capacitor is accompanied by an increase in its resistance to electric current. The capacitor charged from the power supply voltage acts as an infinitely large resistor in the DC circuit, and as a result, such circuit breaks. On the other hand, if we connect the capacitor to an AC power supply, the capacitor will be conducting AC current, which is the charging and discharging current of the capacitor. That is why the capacitor in the AC current can be viewed as a certain resistance, because when charging and recharging, the capacitor accumulates voltage directed towards the voltage of the source. Additional resistance added to the electric circuit by a capacitor is called capacitive reactance, abbreviated as XC. And remember, the higher the AC current frequency, the lower the capacitive reactance. Capacitor's capacitance is measured in farads, and the capacitive reactance in ohms.